Hey everyone, welcome to another video for space design, where we'll be talking a little bit more about the current big development in spacecraft technology and systems engineering, and that's optical communication systems. So as it stands, as we talked about last video, spacecraft are communicated to and communicate back to Earth using different frequencies of radio waves, similar to television or radio in your car or GPS on your phone, things in that frequencies, those frequency waves. As it stands, using this kind of technology, the further you get away from Earth, the signal to noise ratio and speed of the signal decreases dramatically. As it currently stands, communicating a large HD picture as taken by a Mars rover back to Earth in the best of conditions with Earth relative to Mars takes about 7 hours at 5 megabits per second. We'll talk about some of the benefits and research going on into optical communications. And next week, I'll put together another video talking about some of the current experiments and state of technology as it is right now. First, we'll look at the theory, and if we already have a deep space network and the means of communicating by video waves already, why do we want to throw all that away? Well, one of the benefits is the data rate being much, much higher. As mentioned earlier, with someone on Mars or around Phobos or Deimos, you couldn't hope to have an actual conversation with them back and forth. Another benefit is the signal to noise ratio, and we'll talk about why that is theoretically. And another huge benefit is that due to the fact that we position things, we know where our satellite is around Earth or Mars or wherever by using radios on the ground and calibrating it that way. Navigation can be greatly improved and accuracies can be down to a couple of meters if laser communication were to be implemented. So we'll talk about why these properties are the properties of using lasers instead of radio waves. The way I think about it is radio waves are visible light, or not visible light. They're light the same way visual spectrum is, like laser would be, but much, much slower in frequency. Light is on the order of 300 terahertz, while the radio frequency is on the order of 300 kilohertz to 300 gigahertz. So that's about 1,000 times higher frequency. And frequency is the inverse of the wavelength, lambda. So in this chart I have here on the right, you can see that shooting a laser or radio wave or whatever, it's all the same thing. It's all waves with a higher frequency, lower wavelength, like on the one at the bottom, results in a much tighter cone. And why you want that is when you're communicating something as far away as Mars, the cone grows and grows and grows based on that angle theta, to the point where something from Mars communicating back to Earth could have a cone, the diameter several times bigger than Earth's diameter. And that introduces a lot of noise, and a lot of noise from similar frequencies just out in space that makes it, one, take longer to get what you're actually trying to get from the deep space network, and two, makes it harder to actually pull the signal from the noise. With laser communication, it's a much tighter cone, and as you get further away, it scales better because that theta is just smaller. And a way to think about this is, think about a lens on a telescope. The lens on a telescope is focusing stuff that's really far away in the visible spectrum into a narrow, tight cone for you to see, and makes it visible and large. An antenna on a radio is doing the same thing, just for light that you can't see. Currently, and this is talking a little bit about the navigation I mentioned earlier, I spent a summer, 2 summers ago, working for a defense contractor as an intern. And an interesting project they had me work on was seeing how good a prototype satellite they had launched actually was at pointing towards the ground station they were trying to have it point towards. And the way they did this was taking the actual data from the satellite of where it thought it was, where it thought it was pointing, and drawing a straight line from where it thought it was pointing down to the ground. And not down to the ground necessarily, but to wherever it was pointed. And when it was supposed to be passing over, having the end of that laser beam where it touched the Earth superimposed on a map and seeing how far away that was from the antenna, the ground station's antenna, that is. This was then compared to the specs that they had promised their customer for the satellite, the military, and seeing how far they fell short and how much more accurate they could make their satellite a point and remedy that. And I say this is an important thing because there's a lot of imperfections both in the satellite and in the ground station in knowing what they're pointed towards. You can't just see that you're pointing towards the satellite. Satellites are acquired and we know from the ground where they are initially based on an orbital estimate. So they're injected in their orbit and the launch provider provides you an estimate that at this time, they're going to be at this point in the orbit because our rocket is this good at being accurate in setting up your initial orbit. And your rockets or your motors and your engine are this good at putting you in a higher transfer orbit, so on and so forth. Then the antennas on the ground point towards where they roughly think the satellite is from that estimate. And then it's a trial and error kind of thing where you point, you get a certain decibels of gain from where you're pointed, point somewhere else a little bit slightly different, a couple arc seconds away. And you keep doing that until you start seeing it go down. When you start seeing it go down, you go back and you know that that peak is representative by where your satellite is. You're exactly pointing at it. Optical in a number of ways would be a lot better at determining where you are in your orbit, even as far away as Mars, especially that further away. Some of the drawbacks to using an optical system, though, are you have to be keeping your laser pointed exactly at the ground station on Earth or low Earth orbit satellite that you're having then relay that. In this instance, having proper attitude control of your satellite, kind of like the example I was talking about earlier in my internship, is really crucial because with that cone being tighter, if you waver at all in your satellite's pointing, and that error can become complete loss of signal. Similarly, this is a complex, heavy instrument, some of these lasers that could fail really easily. And another thing to consider is things like the clouds around your ground station or even the sun can introduce lots of noise. So there's a number of interesting things to think about. And as it currently stands, there's a number of experiments being conducted in the works to begin development of actual optical communication systems that we can use on spacecraft in the future. We talk about that next time. Thank you guys all for watching.